Hello everyone. In this clip, I would like to show you how to use the wizard capability of GIFMod to create a model of Raingarden system. So this is the diagram of the Raingarden system that we are trying to model. So this basically the model consists of a catchment. It's an impervious catchment where the runoff is generated. And then our rain garden, as you can see here, the rain garden consists of a surface water component, which is represented by a pond, an engineered soil layer, or a topsoil layer, which we're going to discretize into 5 layers, an aggregate storage layer, and then we're going to model the native soil underneath the rain garden system, and we'll also consider the recharge into the groundwater. The rain garden has an overflow and an underdrain pipe that carries the water to a receiving water that can be traditional sewer. The overflow pipe has an elevation of 0.1 above the pond, so whenever the water level in the pond exceeds 10 centimeters, the water flows into the receiving water. And then the underdrain pipe has an elevation of basically 55 centimeters below the ground surface level. Now you can see in this diagram some of the specifications of the model. So we have the catchment has a width of 20 meters, a length of 50 meters. It has an elevation of 80 centimeters above the pond level, so this elevation will be used to calculate the slope, which is used to compute the flow rate using the Manning's equation. We're going to consider engineered soil to be highly permeable and the native soil to have a lower permeability. The area of the rain garden system is 15 square meters. So let's get to start. I'm going to start GIFMod. Okay, let's move it here. I'm going to expand the window so we can see things better. Okay, so this is GIFMod. First thing, I'm going to click on the wizard icon on the top toolbox of GIFMod. So this brings a list of templates that are available. I'm going to move my mouse to the first one, which is the one that I'm going to use to build this rain garden model. So when you move your mouse, you'll see some description about the model. So we're going to choose this, click OK, and this window will show up where we have to enter the information. So basically the first page I assigned to kind of a short description of the model, and you see a diagram of the basically conceptual model right here. Now if you want to see this better, we can just click on the window and it shows us basically the diagram with a larger diagram with more details. So this is the conceptual model. So I'm going to go to the next tab. I can click next or just choose the tab from here, and I'm going to start entering the information. So the length of the catchment, as we said, was 50 meters. The width is 20 meters. The elevation of the catchment, as I mentioned, was 0.8 meters. Now we can choose different units here, as you can see, but I'm going to keep it at using SI units as far as possible. The area of the rain garden, as you mentioned, is 15 square meters. The elevation of the pond, we're going to set it at 0. So the datum or the reference elevation is going to be at the bottom of the pond. The total depth of topsoil, as you can see in our diagram here, is basically 50 centimeters or 0.5 meters. So we go back here and enter the value 0.5 meters. The default number of layers for the engineered soil is 5 layers. I'm going to keep it at 5 layers, so I'm not going to change the number of layers. The depth of aggregate layer is 0.3. The depth to groundwater is 2 meters. And the elevation of the receiving sewer line, we're going to assume it's minus 0.6. So the sewer line is basically 60 centimeters below the pond surface elevation, or ground surface elevation. So now let's go to the next tab. So this tab includes some physical properties of our system. So the first question is about the Manning roughness coefficient of the catchment area. I'm going to use 0.011, and then we have to choose the type of soils. So the first one is the engineered soil. So I'm going to choose a soil type that is highly permeable. The one with the from the drop down list, I can see that the one with the highest permeability is sand, so I'm going to pick sand. Please note that based on this selection, some default values are assigned to the hydraulic properties of the soil, including Van Genekten parameters and hydraulic conductivity, but then we can always go and change those values later on after the model is created. For the type of native soil, I'm going to choose a low permeability one. I'm going to go with silty clay in this case. So this is done. Now I'm going to go to the next tab. These are the properties of overflow pipe. So the things that we need, first one is the diameter of the pipe. I'm going to assume this is a 6-inch pipe, so I'm going to type 6, and then I'm going to change the unit to inch. The length of the pipe I'm going to assume is 8 meters. We also need the Hazen-Williams C factor for the pipe. At this point, I'm going to keep it at 100, which is a default value. And then we need the pipe's start elevation. So this is the elevation at which overflow starts to occur. So I'm going to use 0.1 meters for the pipe start elevation for the overflow pipe. And then please also note that whenever a unit is not present for a quantity, that means SI units are going to be used as default. So then these are the properties of the under drain pipe. The diameter of the pipe, again, I'm going to assume 6 inches. The length of the pipe, I'm going to assume 8 meters again. And the Hazen-Williams factor, I'm going to keep it at 100. And the pipe start elevation is minus 0.55, as you saw in the diagram right here. So that's the elevation, minus 0.55 meters. So with that, I'm going to go to the next. So here we're going to enter some climate data. So there are some boxes for solar radiation, humidity, and temperature. These are needed if we wanted to also consider evapotranspiration. At this time, I'm going to basically ignore evapotranspiration effect, so I'm not going to enter any time series for time series data for these three items: solar radiation, humidity, and temperature. Okay, let me expand this a little bit. Now we need precipitation time series, so I'm going to click on this box right here, and it asks me to provide a data file containing the precipitation time series. So I've prepared the precipitation time series before, which I'm going to use. Now I need to go somewhere where I've saved this. So Raingarden data, and I've the format of my precipitation data is in a CSV form. So I'm going to change this extension to a CSV, and I'm going to click on the file called rain.csv and choose that one. So then we also need to provide the duration of the simulation. So the rain data that I provided covers year 2010. That means from January 1st, 2010 to December 31st, 2010. So I'm going to set the duration of simulation from January 1st, 2010 to January 1st, 2011. So this completes the all the information that is needed to create the model for the Raingarden system. Next, I'm going to go and click on this bottom create model, and the model will be created. So I have the model created, and now let's do some inspections before running the model. So I'm going to close this window, zoom out a little bit, and we can click on some of the blocks to see if all the properties are assigned correctly. So this pipe has a diameter of 6 inch, and the start and end elevations are set correctly, and the Hazen-Williams constant and length and so forth. This connector is the connector between the catchment and the pond. So as you can see, the Manning roughness coefficient is assigned correctly, and the width and so forth. So I think the model is ready to go. So what I'm going to do is that I'm going to save it. I'm going to save it as with this name, Raingarden_test. Save it, and I'm going to run the model. Running is going to take some time. So the first GIFMod checks all the blocks to make sure that all the information that is needed is provided, and it seems it has. Now this window, this essentially simulation progress window shows up, and the graph shows the time step values as they change with time. We can also click on this bottom, shows solution details, and it shows us some of the things that are happening, mainly the reasons why the GIFMod basically reduces the time step at different times. So I'm going to close this to make this go faster. So let me point out here that the time step values that are shown on this graph are in days. So our average time step, I would say, is around 0.04 days. That's the time step under which the solver becomes stable. But then what we expect is during the rain events, the model will automatically pick smaller time steps, and during the dry times between the events, the model uses larger time steps. Okay, so the simulation is almost 93% done. 94%, and so it's almost complete. Okay, it seems that the simulation is finished. It takes a while for the results to be written in some text files. Okay, simulation finished. Click on this one. I'm going to close this window. So this simulation took 540 seconds, which is less than 10 minutes. So I'm going to close this, and then we can inspect some of the results. So the first thing, let's look at the flow that is basically enters the pond. So I can just right click on this connector that connects the catchment to the pond and click on, so I have two screens. The graph went to my second one, but this is what you have here. So this is the flow. By the way, we can also look at the precipitation, the data that we entered. So if I click on settings and climate settings, the precipitation data file is right here. I can right click and click on flow, and it shows me the precipitation intensity. And so we close this one. So this is a flow. Let's look at the let's see how frequently an overflow took place. Click on this one. So this is it seems that overflow happened a few times during the year, and we can also look at the under drain. So this is the under drain flow. So almost during every rain event some underflow took place. We can also look at the moisture content of the soil. So I'm going to click on one of the blocks and look at the moisture content. So this is the moisture content of the soil. Let's look at the recharge into the groundwater, which I expect to be small, considering the fact that my hydraulic conductivity of the native soil is quite low. So what you can see is that you see this negative flow at the beginning. That's due to essentially soil suction. Basically takes up water from the groundwater. But we can zoom, and so it's almost zero. Our hydraulic conductivity of the saturated hydraulic conductivity of the soil is pretty low. It's 0.0048 meters per day, and that's it. Thank you for watching. Have a great day.